Hello and welcome to my YouTube channel. This is Ramani Online Mathematics. If you know you have not subscribed, please subscribe, share to your colleagues. Let's continue with wave equation. Here, there's a beautiful question on the board. You have to solve this wave problem. UTT equals 4UXX. Boundary condition is given. Two initial conditions are also given. So let's see what we can do. So first thing, we should know our UTT to be equals to 4 UXX. So for that matter, the boundary condition has already been given, which is x of 0 is what? So look at this one. The boundary condition is x of 0 to be 0. This time around, it's not pi, it's 1. X of 1 to also be 0 is 0 and 1. Is that okay? So let's see. Let's differentiate. Let's take our this thing, which is xt. So I'm going to have UTT to be xt prime prime. Then UXX to be x prime prime t. Let's substitute. So I'm going to have xt prime prime equals 4 x prime prime t. So what I'm going to have here is simple. From here, I can say that x prime prime over x is equals to t prime prime over 4t equals lambda, which means that x prime prime minus lambda x equals t, 0. Then t prime prime minus 4 lambda t is also equals to 0. Now, we pick this one and we study the cases, all the three cases. Then here we consider only the third case. So here, I'm picking this one, case 1. When lambda is equals to 0, what happens? If I put 0 here, I'm going to have x prime prime equals 0, right? Because 0 times x will go to 0. So, and if you do integrate this one 2 times, you see what? You are going to have ax plus b. Is that okay? And if you solve this, this is going to, will this one give us a trivial solution? Let's check and see. When x is 0, capital X2 will be 0. So I'm going to have 0 equals a multiplied by 0 plus b. These are my b is equals to 0. If b is 0, this is 0. Now let's move to the second one. If x is 0, small x is 1. So I'm going to have 0 equals a times 1, which is a because here is 1. So that one will give us, so a2 will be 0, okay? And since a is 0, b is 0, this gives us a trivial solution. So we move on to the next. That's case 2. So let's look at case 2. That is when lambda is greater than 0. What happened? He said that we should let lambda to be equal to p squared. So from here, x prime prime minus 4p squared x equals 0, which means my r squared minus 4p squared will be equal to 0. So my r will be equal to 2p. Is that okay? I'm rather using the t. This place shouldn't be like that. So let me correct it, okay? For the x, there's no 4 there. So it's supposed to be x prime prime minus lambda x, okay, equals 0. And now our lambda is p squared. So I'm going to have x prime prime minus p squared x equals 0. So I have r squared minus p squared equals 0, right? So this is what you're going to have. So I'm going to have r to be equal to plus or minus what? P. So the solution becomes x of x equals a e to the power px plus b e to the power negative px. The reason why I'm writing this one directly is that I've explained to you in my previous video when you look at the heat equation when I was solving it. Now let's move on. I have ax, let with the t. Sorry. Yeah. I don't know why I'm rushing to. Now this one, you test again with 0 and 1 here. And when you do that, the first one, this will be 0 equals a plus b. Why is it a plus b? Capital X is 0. Small x is 0. So if I put 0 here, to be e to the power 0, which is 1. E to the power 0, which is 1. So I left with a plus b. What it means is that my b will be equal to negative a. Or a is equal to negative b. Now, if that is the case, let's move to the second one where the capital X is 0 and x is 1. Small x is 1. So I'm going to have, 0 equals, already we have a e to the power p, because x is 1. P times 1 is p, plus b e to the power negative p. But you know that negative b is equals to negative a, so I can say that a 0 is equals to a e p minus a e negative p. So which means that I can have 0 equals a outside ep minus e negative p. Now for this case, there's no way that this condition, in fact, exponential function can go to 0. It can never happen. So the only way we can say that a is equals to 0, but e to the power p minus e to the power negative p is not equals to 0. If a is 0, automatically b also becomes 0. Have you seen that? So when that thing happens, we say that this is also yielding with trivial solution. So we move on to the case number 3. Let me clean this side again for case 3. Case 3. What is case 3 saying? You say that this lambda is less than what? 0 means that we should let lambda to be equal to negative p squared. I've explained where this negative p squared is coming from. Now, if you're able to do that, that is very simple. You are going to substitute here x prime prime minus lambda x equals 0. I have x prime prime minus lambda x. So lambda is now this negative p, so will become plus p squared x equals 0. So my r squared plus p squared will be 0. R squared equals negative p squared. My r will be plus or minus pi. In fact, all this explanation, you can find it in heat equation. I've said this is the same as the heat equation. Just that here we are taking them two to each two. We have UTT and UXX. By heat equation is UT and UX. So that's why I'm moving straight. How do you write the equation for this? The equation for this one is going to be A cos px plus b sine px. So this is what we are going to have, right? After getting this, you know what to do. If you do the substitution here from this place, my capital X is 0, so 0 equals a, my small x2 is 0, okay? If I put 0 here, cos 0 is 1, sine 0 is 0, so it means a is 0, okay? Let's test for the other one. My capital X is 0, a is always 0, so everything goes to 0. B sine. Now px, the x is 1 here, okay? So here I will have sine p. As usual, we say that sine p is rather 0 and b is not equal to what? 0. But he said that we should take p to be equal to what? N pi. Okay, it means that wherever I see p, I should put n pi there. Okay. Now, let's go and do the substitution. And we say that where n equals 1, 2, 3, going. Let's do the substitution and see something. We are coming back here, so I'm going to have this equals A is already 0, so everything here goes to 0. B, then put n there because of the n. Bn sine. Now this p is now n pi, so I'm going to have n pi. There's already x here, x. So this is what we have as our x. Now I lay with t, so let me write it somewhere here. So my x of this equals Bn sine n pi x. So that is that. Let me underline so that. Let me clean here and go for the t. For the t, you only consider the third case. It will have t prime prime minus 4 lambda t equals 0. So here is going to be r squared. In fact, the third case is saying that lambda is less than 0. So you let lambda to equals negative p squared. And you say that because we are using n, let's take it straight away from here. So instead of using p, we are replacing by n. So I'm going to have t prime prime plus 4n squared t equals 0. So from here, you're going to have r squared plus 4n squared equals 0. My r will be 2 ni. Is that okay? 2ni. If you send this way, it become negative. If you take square root of a negative number, it gives you complex. That's why the I is coming in. So let's move on. How do you write the solution of this? This is going to be t of t equals a cos 2nt plus b sine 2nt. So that is the solution for that. So this one, you can't do anything about it. So we maintain it, which is t of t is equals to a cos 2nt plus b sine 2nt. So that's why we have. But remember, we need u equals xt. So my u will be equals to, this is our x. Our x, we had bn multiplied by sine n pi x. And the whole of this is multiplied, this is multiplied by the whole of this. A cos 2nt plus b sine 2nt. So this is what we are having now. So here, if I multiply through, look at what I'm going to have. I'm going to have my u to be, this is b and this is a. They are all constant, okay? So constant means let's represent it by a n, just like what we did for the first one. So here we're going to be a n multiplied by cos 2nt sine n pi x, then plus bn multiplied by b. That will also be a constant. So let me replace that one by bn. Then I have sine 2nt multiplied by sine n pi x. So this is what I have. And I said that you can put this one together using the summation because you know that the n is sum from 1 to infinity. So let me use blue pen here. I'm going to have my u to be equals. So let me write it here direct. U is going to be summation n to n equals 1 to infinity. An cos 2nt sine n pi x plus bn sine 2nt multiplied by sine n pi x. So this is what I have for my u. I need to find an, then also what? Bn. And that one will bring us to the initial condition, the two of them. So let's start with the first initial condition. Let me clean here. Okay, so for the first initial condition, x is x, t is 0. f at x is, or u is x bracket open 1 minus x. Is that okay? So let's do that. So let's see if I substitute. So u is this. So let me put it there. X times, let me expand this. X times 1 is x. X times this is negative x squared. So I'm going to have x minus x squared equals t is 0. Can you see that? So if t is 0 here, cos 0 is 1. So here I live with an sine n pi x. An sine n pi x. You know here, if I put t to be 0 here, sine 0 will be 0. So everything here goes to 0. So this is what we have. So I have to look for what? An. And this is Fourier sine. So I'm going to have an equals 2 over. Now let's see. Where is the limit? It's from 0 to 1. Is that okay? So that will be 2 over 1. The integral start from 0 to 1. F at x, which is giving us x minus x squared. Then sine n pi x dx. So that's why you're going to have. So you have to integrate this. Using integration by part, here will be u v x minus x squared. If you differentiate this, we have 1 minus 2x. If you differentiate this, we have minus 2. This gives you 0. We have sine n pi x. If you integrate this, we have negative 1 over n pi cos n pi x. Then if you integrate this again, you have negative 1 over n pi squared sine n pi x. Here I differentiate 1, 2, 3. So 11 with 1. This gives you positive 1 over n pi cube cos n pi x. So you're going to have this. So plus minus plus. So this is what you're going to get. So since we have this, let's see how we can form it. So our an now is going to look like this. 2 over 1 is 2. This multiplying by this, right? Remember there is negative affecting this. Plus meeting negative. This gives you what? Negative. So the negative multiplying this is going to give us x squared, because the negative multiply here become positive, minus x all divided by n pi. Is that okay? Cos n pi. I'm done with that one. Then I'll move to the down here. Negative meeting negative, that become positive. So what I have left here is plus 1 minus 2x over n pi squared sine n pi x. Sine n pi x. Now the last one, negative 2 multiplying this by here is plus, will still be negative. So this side is going to be negative 2 over n pi cube cos n pi x. And this one is starting from 0 to 1. Wow, that's the integration of it. Now let's substitute. If I put 1 here, I'm going to have my an to be equals to, I'm going to have 2 outside bracket open, 1 minus 1, which will give you 0. So it means that automatically here goes to 0. And 0 multiplied by this, it will give you 0. If I put 1 here, it will be 1 minus 2. But remember, here is n pi x. So even if I put the x, the 1 here, that will be sine n pi. Sine n pi is also 0. So this one will also go to 0. If I put 1 here, this will be n pi x. So n pi, because n pi is negative 1 to the power n. So what I'll be having here is negative 2 over n pi cube to the negative 1 to the power n. Then minus, if I put 0 here, everything here goes to 0. If I put 0 here, sine 0 is 0. Okay. If I put 0 here, I'm going to have 2 over n pi cube, cos 0 is 1. So this is what you're going to have at the end. So you should take note of this. If you put 1, here will be 0, here will be 0. Sorry, 1 minus 1 will be 0. That makes everything goes to 0. If you also bring 1 here, sine n pi, this is n pi x. So n pi x is 1. So that will be sine n pi. Sine n pi, you have established that it is what? 0. If I put, so everything here goes to 0. If I put 1, 2 here, this will be cos n pi. You know cos n pi is negative 1 to the power n. And this one maintains. The same thing applies to the 0. If you put 0 there, that's what happens. Okay. This is what we have now. Let's see if you can do simplification. So here I can have 4 minus 4 negative 1 to the power n. And this is divided by n pi squared. So this becomes my an. I just multiply through and I brought this one to this side, this one here, so that it will look nice. So my an is 4 minus 4 bracket to negative 1 to the power n, all divided by n pi squared. Let's move to the bn. Right, so now let's look at the ut. We are done with this initial condition, so we are moving to the ut. And that one means we need to differentiate this one with respect to t. So sine n pi, that one is constant. Cos 2nt is what you are differentiating. If you differentiate cos, you get negative sine. And you know this one, if you differentiate this with respect to t, let with 2n. So here we are going to have ut to be equals to summation n equals 1 to infinity negative 2n an sine 2nt. Is that okay? Then sine n pi sine n pi x. So you are done with this side. Class, you are now going to integrate the next one. Sorry, differentiate. If you differentiate this with respect to t, sine, if you differentiate sine, you get cos. We are going to have 2n bn cos 2nt sine n pi x. Please, because of the space, that's why I have done it this way. Okay. So when you do the differentiation, this is what you have. Now, they are saying that ut is equals to cos x. So wherever I see ut, I should put cos x there. Cos x. Also, x is x, t is 0. So if I put 0 here, sine 0 will be 0. So everything, you know, this is multiplying this, so everything here will go to 0. If I put 0 here, cos 0 is 1. So what I will have left will be 2n bn sine n pi x. Is that all right? Good. So this is what I have. Now the next thing that I have to look at is able to find bn. Okay. And this is Fourier sine. So for you to be able to find here, you know that you take the coefficient of the sine n pi x, which is 2n bn, is equals to 2, because it's 2 over 1. The limit is from 0 to 1, right? It is here 0 to 1. Then the function is cos x. Then sine n pi x. Remember, it's Fourier this thing. Now this one, let's the whole of this is cos x sine n pi x should be equals to, I know what I'm doing. Let's the integral of cos x sine n pi x should be equals to I. Let's represent the whole of this by I, okay? So let's differentiate, integrate this u v. I'm bringing my sine n pi x here, and I'm bringing this side to be cos x, okay? Now sine n pi x is going to be, in this one I'm differentiating, so I'm going to have n pi cos n pi x negative n pi squared sine n pi x. Now let me explain this thing to you. Somebody may ask, at which point will you pause? Because you see, this one will never terminate. We have done something like this in our previous videos when we are looking at neither even nor odd. The point where you pause is, you see, this started with a sine. So when you differentiate and you get to where the sine is, you stop. So the same thing applies to this. This is cos x. If you integrate cos x, you get sine x. If you integrate sine x, you get negative cos x. So cos x. You see that? So now this one is going to this way. This one will go to this one. And this, the last one now, because this one is not terminating in the normal sense, this one has to take the next integration of the cos, which will give you sine. But what happened here is that because this one is not terminating, it means that it's keep on, or the integration is continuing. So I will map the last one to this one again. So this, the minus sign is affecting this. So this is plus, minus, plus. Is that okay? Good. So this is what we have. Now I said that I should let this should be represented by what? I. Let's forget about the 2nbn and the 2. It will come. So I have I is equals to, so it will be this times this. This is positive. This one too is positive, right? So that is going to give you sine x multiplied by sine n pi x. Then this one go here. This is negative. Here too is negative. So and again, that will give you positive. So plus cos x multiplied by, so let me bring the n pi out here, because there's n pi here, multiplied by cos n pi x. Then the last one is going to be plus, because this is negative, multiplied by another negative here. There's negative multiplied by negative. That will be positive. Now the last one, you see that it's coming back to this. So you bring the integral sign again. So here is going to be integral of You see, this is constant, so I can bring it out. So n pi squared integral of cos x sine n pi x dx. Now let's look at this one. This integral sign we have here is the same as this one. Can you see that they are the same? So in place of this, I can move the whole of this and replace it by what? I. So don't be confused. So the whole of this, I'm going to replace by what? I. Because they are the same. So now grouping like terms, there's I here, there's I here. I can send it there. If I send it, I'm going to have I minus n pi squared is equals to sine x sine n pi x plus n pi cos n pi x cos x. Is that okay? So this is what I have. I will not clean this one because I'll use it later. So I'm coming back here. Now here, there must be I here because there's I there. Here, there's I here, I here. If I factorize I out, I'll be having 1 minus n pi squared. 1 minus n pi squared. This is what you have, right? Then it's equals to sine x sine n pi x plus n pi cos n pi x cos x. So this is what we have. Now we want the I to stand alone. So we say that I is equals to sine x sine n pi x plus n pi cos n pi x cos x. Is that okay? All this is divided by 1 minus n pi x. So this is what we have. Remember the I is the same as this. Is that okay? So I is this, right? If I is that, what are we going to do? Already, there was 2 multiplying by this. If you have forgotten, it was 2n bn is equals to 2 multiplying by the whole of this. This is how it was. So here, if I divide 2 by 2n, I'm going to have bn equals I over n, like this. I hope you understand that one. Okay. So let's see. So this is what I have. I over what? N is equals to, is equals to, now, this I is the whole of this now. And the limit was given from 0 to 1. Is that okay? So I'm going to substitute. If I put 1 here, I'm going to get 0 because sine n pi x is 1, so it will be sine n pi is 0. 0 times sine x will be 0. Now n pi cos n pi x. Cos n pi is -1. So here I'm going to have -1. Let me bring the n pi first. N pi negative 1 to the power n cos 1, because this is cos 1 x, so cos 1 minus, now if I put 0 here, sin 0, everything will be 0. Is that okay? And here too, cos 0 is 1. Cos 0 is 1. So here I have minus n pi. And the whole of this is divided by 1 minus n pi squared. Is that okay? Good. I've taken some n pi away. Please, this place is supposed to be 2n pi. Okay, so when I divide here, with n pi. So now remember this I is with n pi, so here too there will be n pi here. Since I have I over n pi, and the top one, all this side is n pi divided by n pi. So this is what I have. So I'm going to have that n pi is multiplied by this. So I'm going to have, if I factorize n pi out, you see it will cancel this, leaving negative 1 to the power n cos 1 minus 1, all divided by 1 minus n pi squared. And this gives us bn. So this is our bn. Finally, bn has arrived. So we have our bn to be this, an to be that. So all you need to do is that you come here, wherever you see an, you put the whole of this into it. And wherever you see bn, you put the whole of this into it. And that gives us our final answer to that question. Is that okay? Thank you very much. But how this thing has been integrated, practice more and you understand more. Thank you.